Okay, so now according to the time schedule, so it's a time for the presentation of the Professor Ahmet Enis Cetin. The title is the Energy Efficient Signal Processing and Machine Learning Algorithm. So Professor Cetin, he got a PhD degree from the Ankara. So, and also he got the master and the PhD degrees from University of Pennsylvania in 86 and 87, respectively. So Professor Cetin, he has a very impressive CV and the curriculum. So he's the IEEE fellow, and also he's serving as the editor-in-chief for also editor board for several journals. So especially the journal that we can say he's serving as a chief editor is a Signal, Image, and Video Processing. So Professor Cetin, so the floor is yours. So if you are ready, so we are looking forward to listen to your presentation. So you can share your screen if you are ready.
Okay. Just a second. Okay, so let me also, I thought they are going to present my slides. So let me also share my slides. Okay. Just a second. Okay, so energy efficient signal processing and machine learning algorithms. My interest to this area started when I was designing this camera. This is a camera, okay? So it looks weird. It's designed in 2004. It's a wide-angle camera, and it has an ARM and a GPU inside. So it's a wide-angle camera, so it receives this wide-angle fisheye image, and then it corrects it and generates this panoramic image and produces the panoramic image as the output. This is mainly due to the GPU inside the camera. And the camera was successful. There is this company that I co-founded, and it's received even some press items. And the problem is that we have to cool the GPU. You see the cover. This is a video recording unit, and it has a lot of coolers. That's why the aluminum case became much more expensive than the electronics, and it was expensive and hard to produce this aluminum case just to cool down the system. So the current vehicles have to use GPUs, and they consume a lot of power. And so I will describe energy efficient image processing or video processing algorithms in this talk. What happens is that we introduced an operation to replace the multiplications. Multiplications consume a lot of power in processors. And so to multiply two numbers, quote unquote multiply two numbers, we have, let's say, two real numbers, x and y. We determine their sign, x times y, and then we take the absolute value of x plus y. This is inspired by the fact that x times y is equal to sine of xy multiplied by absolute value of x times absolute value of y. Okay, so we replace the multiplication sign here by plus. So 2 times 3 makes 5 in our notation. And 1 times -3 becomes -4. This approach is used in signal processing, or related approaches are used in signal processing. There is the sine LMS adaptive filtering algorithm introduced in 1980s. In fact, the LMS algorithm, adaptive filtering algorithms are used in modems and everywhere. And they are the predecessors of neural networks. So our operation is multiplication free because sine xy can be calculated by using the sine bits of xy. And then we have additions. Once we have the sine x, this multiplication, we can define inner products like this: x transpose y is equal to summation I sine xi yi, absolute value of xi plus absolute value of yi. So this is a vector product here. X transpose y is equal to summation I xi yi. This operator has some properties. It's L1 norm. It induces L1 norm. So X transpose operator X, the regular dot product induces the L2 norm. So in this case, X transpose X is equal to summation I sine xi absolute value of xi plus absolute value of xi, and it's just 2xi. Now, the idea is that we can use this operator in neural networks and other machine learning algorithms. Okay, in other machine learning algorithms, we can build a covariance matrix similar to the regular covariance matrix. Instead of multiplication, we now use this operator. Unfortunately, this matrix, A matrix, may not be positive semi-definite in general. So it is not a Mercer type kernel. It does not introduce a Mercer type kernel, but we developed neural network algorithms and other machine learning algorithms based on this operator, and it works. Recently, we developed another version of this algorithm, and we have now the kernel property. So we have a well-defined mathematics behind it. So this is the new operator. X operator y is equal to sine x times y, minimum of absolute value of x and y. So in this case, we have 3 times -1 is just -1. 2 times 3 is 2. So what happens is that we just consider these 2 and 3 as sets, for example. The intersection of 2 and 3 is just 2. Okay, and 3 and -1 does not intersect. Therefore, I have a -1 here. And in terms of their magnitudes, the amount of non-intersection is -1, negative or +1. So we have -1. So that's the idea behind this new operator. And we can generalize it into the vector form. X transpose y is summation I sine xi, minimum of absolute value of xi, yi. We have a theorem. This is a Mercer type kernel. It generates a positive semi-definite Gram matrix. In other words, I have this kernel. There is a kernel operator, kxy, which is equal to phi x, phi y. So if you are given two vectors, x and y, then we have a function mapping the x to another function, phi x, and there exists another function, the same function, phi, takes the vector y to phi of y. Then in the new domain, you perform a well-defined dot product. And that dot product happens to be equal to summation I sine xi yi minimum of xi yi. I'm going to show you how this phi looks like in my next slide. So this operator satisfies the reproducing kernel Hilbert space framework, and it has the L1 norm property x transpose dot, or x dot x or x transpose x is just the L1 norm. Okay, the other one was generating 2 times the L1 norm of x. Now this is generating just the L1 norm of x, which is, you know, the determined by the summation x absolute value of xi values. So it's a new operator. I'll skip the proof. So we have, let's say, x's and y's. We have 2 classes of data in this figure. We have this function phi. This maps the x's and y's to another domain. And this is the reproducing kernel Hilbert space domain. And in this new domain, we can develop machine learning algorithms using phis, or in fact, I have the formula for phi here. We can find it, but you don't need to use this phi. In fact, it's not practical because it's infinite dimensional. So you just convert the x's to infinite dimensions. So instead of generating these using these infinite dimensional functions, we just use this computable kernel dot product, which is summation I sine x I yi minimum of absolute value of xi times yi. And it's computable and it doesn't consume energy, because it's based, minimum calculation is based on additions and subtractions, subtractions and comparisons, and sine xi yi computation is just a bitwise operation. And then we have the additions due to this summation operation. Okay, so that's the idea of this energy efficient operator. And then you can build neural networks based on these operators. In fact, there are also other versions. For example, we can come up with this. It induces the LP norm. So we are currently working on these. You can construct covariance matrices. You know, the covariance matrices are used in a wide range of machine learning algorithms. So instead of using 1 over n minus 1 x transpose, you have lots of matrix multiplications in x transpose. Instead of that, we get the covariance, quote unquote, a kernel covariance matrix without performing any multiplications. And then you can carry out eigenvalue, eigenvector decomposition to generate machine learning algorithms. So this method is also robust. That's an interesting property of this because of the L1 norm. So let's say you have this data, it's a toy example. If you just apply the regular principal component analysis, you get this black line. There are robust principal component analysis methods, for example, and that gives you this red line. And our methods goes through the center. Okay, they go through the center of this data. And this data is, this is because of the L1 norm property of our operators. In fact, I referenced the neural networks papers that we recently had. So, for example, this is our latest neural network paper. In this paper, you have convolutions in neural networks. So you can construct convolutional neural networks. Instead of performing multiplication, you just perform the dot product, our dot product. You can even construct this transformer neural network using our operator. It works, everything, because it's a well-defined, we have a well-defined mathematics behind it. It's a kernel covariance matrix, and it produces robust results. So I have here the regular convolution expression. So you replace the multiplication here with our operator, and you get YMN based on our operator. Now, the question is, can we train such neural networks? The answer is yes. We do some approximations here because we have to take the derivative of this convolution or the dot product, and the derivative is doable because the derivative has impulses, and this is the Dirac delta function because of the sine operator. Sine, the derivative of sine produces impulses, but we approximate the impulse with a Gaussian, sharp Gaussian. And that's how we train the impulse. And one disadvantage of the operator is that the training takes longer than the training of a regular neural network. But in many applications, the training is done offline. Therefore, you can get neural networks. One problem is that another problem is that in neural network, there is something called batch normalization. So we have to use also the batch normalization. You normalize everything by this batch normalization is used during the training or implementation. You have to normalize by the variance. So we do that, and it's our networks are not completely multiplication free, but the amount of computation is significantly lower than other networks. So these energy efficient networks can be used in practical applications, including autonomous driving, because they don't use energy consuming multiplications, and they can be implemented using simpler processors, and in fact it can be possible to develop even GPUs performing based on this simple operation. Okay. Thank you very much, and that's all that I want to talk about. I think my time is also out.